Hi, I'm Marvin, and in this video, we'll be going over some of the physics involved in headspins and how you can improve yours should you ever attempt them yourself. The topics we'll be exploring in this video are angular displacement, angular velocity, angular acceleration, angular momentum, rotational inertia, torque, and friction. If you've ever seen someone doing headspins, you'd be amazed with their ability to rotate so quickly yet with such control and precision. The physics behind this amazing move is no different than how you're able to control your angular velocity while spinning around on an office chair. Now, what do we mean by angular? In Physics 1A03, we covered topics such as displacement, velocity, and acceleration. Angular simply refers to these vector quantities in rotational movements and consists of very similar formulas. Angular displacement is the angle in which an object travels through. Because displacement is in a circular motion, we measure displacement in radians rather than meters. Hence, angular displacement is our change in angle, denoted by delta theta. Angular velocity is a change in angular displacement over time, and is denoted by omega. And angular acceleration is our change in angular velocity over time, denoted by alpha. With this knowledge in mind, we now have a much better understanding of describing the motion of headspins. However, even more amazing than continuous headspins is the transition of headspins to the headspin drill. In this maneuver, the dancer quickly changes their angular velocity without the aid of any external forces. This is best explained through our previous topics as well as angular momentum and rotational inertia. Here, we have two examples to help demonstrate the difference between headspins and headspin drills. To rotate, both dancers apply a force using their arms and legs that causes them to temporarily accelerate in a clockwise direction. This force in rotational physics is called torque, a force applied to an object some distance away from the axis of rotation. Despite roughly the same amount of torque generated, the same coefficient of friction, and the same mass, our first example shows a much greater angular velocity. The difference is the distance the legs are from the point of rotation, and where angular momentum and inertia come into play. What is momentum? Momentum quantifies the motion of a mass. Like linear momentum, angular momentum is conserved, meaning without any external forces acting on the system, angular momentum is constant. Rather than P equals mv for linear momentum, the formula for angular momentum is L equals I omega, where I equals inertia, the degree to which an object will resist angular acceleration, and omega is your angular velocity. There are many different formulas for inertia, but they all depend on some measure of the object's distance from the axis of rotation. This could be a rod's length, a disk's radius, or a point mass's distance from the center. To keep things simple, let's consider the left foot of the dancer to be a point mass of 2 kilograms. The inertia for a point mass is I equals mr squared. In our first example, our foot is only about 0.1 meters away from the axis of rotation, while in our second example, it's around 0.7 meters. As you can see, inertia is much higher for a mass farther from the axis of rotation. If we ignore the external forces of friction and air resistance and assume angular momentum to be constant, we can see the inverse relationship between inertia and angular velocity, where an increase in one causes a decrease in the other. We can substitute our inertia formula into our formula for angular momentum, and also find an inverse relationship between radius and angular velocity. Of course, external forces do act on our system in real life, but the inverse relationship between radius and angular velocity remains. In our example of headspins to headspin drills, we see that when he brings his legs in closer to the axis of rotation, his angular velocity increases due to the law of conservation of angular momentum. So how could you spin faster if you were to attempt headspins? 1. Bring your legs in closer to your body to decrease inertia. 2. Apply a greater initial torque with your arms and legs. And 3. Practice wearing a helmet or beanie on a smooth surface to decrease kinetic friction. You've already got the physics down, so all you need to do now is practice.